A couple of years ago, I decided to build an electric motor from scratch, mostly because I needed a demonstration model for an explanation video, but I always kind of hoped that it would be powerful enough to drive some actual load. Now, I did get that motor to work. I also made an electronic drive for it, and it ran pretty smoothly, but it wasn't really powerful enough to do anything with, except for maybe like driving a fan or something. So a while later, I built another electric motor. I built this thing. Oh. This was my Mk3 homemade electric motor. It looks a lot more like a proper motor. I spent a lot of time building this thing, and actually a lot of money too, to get all these metal sheets laser cut. It was a pain to build this thing, but it was actually powerful enough to propel an electric skateboard with me on it. I also built a new electronic driver for this thing that was a lot better than the old one. Now, the problem with that is that even though it moved the skateboard with me on it, it would only do so on relatively flat surfaces, so it couldn't go off-road, and it especially couldn't go up hills. And so that's why at the beginning of this year I decided to have another go at this, which is when I built the Mk3 switched reluctance motor, which I've already made a couple of videos about building it and testing it on a test bench. But we haven't properly tested this thing yet in a real world scenario, and so that's what we'll be addressing in today's episode. Right, so we're finally here. It's time to test the new homemade electric motor. It's right here. It's bolted onto my electric skateboard, and now I'm going to go for a ride on it. So this skateboard has existed for a couple of years now, in various forms, and it's kind of turned into a testing platform for homemade electric motors. And the reason I like it for that is because this thing is actually kind of difficult to get moving. It's heavy, the wheels are relatively small compared to something like a bicycle, so it actually takes quite a bit of force to get this thing to move, even on a flat surface like this. So that makes it a real challenge for an electric motor to move this thing, which is exactly what you need if you're testing motors. So why don't we take a closer look at the specific hardware that we're testing today. So, this is of course the new electric motor, the Mk3 switched reluctance motor that we've got on here. And it's driving the wheels of a skateboard through a two-stage drivetrain. So first of all, there is a pulley system here from the motor to this intermediate shaft, I guess you could call it, down there, and there is a chain that drives the rear axle, and that gives you a combined gear ratio of about 18:1, which should be plenty to do some off-roading, assuming that you have a capable enough motor. The type of electric motor that we're using is, of course, once again, a switched reluctance motor. So if you look at this motor from the inside, what you find is a stator that looks very similar to that on other brushless motors you might be familiar with. It's got a bunch of coils on it, but then the rotor is this sort of gear-shaped piece of steel, which crucially has no permanent magnets on it. And then by energizing the coils on the stator in a particular order, you can get the steel rotor to rotate. While this is in some ways kind of similar to other types of brushless motors that have permanent magnets, it's also quite different. Because, for example, if you look at how the windings in this motor are connected, they're not connected to each other in a star or a triangle type of connection. Instead, they're completely independent, so they all have their own connections to the controller, which is also why we have 6 power wires going from this controller to this motor. Then the electronics that are driving this motor are in this box here, and that's still the same drive that I used last time, because honestly it just worked fairly well and I had no problems with it. and it's all being powered by a 6S LiPo battery in here, which is about 24 volts. So it's powering the drive, and then the drive is powering the motor. Now, one of the big problems with the previous homemade electric motor was that it wasn't quite powerful enough to propel the skateboard through rough terrain. Guess what the skateboard is on right now? So let us find out if that problem has been solved. Ah! I got wheel spin there. There it goes. Look at me, cruising along on my electric skateboard. So one of the other big problems we had with the previous motor is that the skateboard wasn't able to climb hills. So to test this, I found a pretty steep hill. I don't know how steep exactly, I reckon it's about 10-12%, something like that. It's not a very big hill, we don't have very big hills around here. But there's a bit of an issue, right, which is that, what if it doesn't make it? What if it doesn't make it up the hill? I don't have any brakes, I will start to roll back, which is why I've made this. See, I've got this log, it's going to be tied behind the skateboard. In case it stops working, it rolls back, I simply stop. How amazing is that? Right, let's give this a go. Turns out I do need the log. Hang on. Just fix this. There we go. Oh! Actually, it seems to be a mechanical problem there. Something just slipped here. The motor is doing okay. Oh. There we go. Right, so we made it up the hill. It was not very smooth, it was a little chaotic. It stopped working a couple of times. I think what happened is, if you look here, you see this sprocket is held onto the shaft using these two nuts here, so it's just squeezed in between. And a couple times the shaft was actually able to spin in there. Now, it seems to be stuck again, so I think the problem has resolved itself. There used to be a grub screw in here to prevent that from happening, but the thread on that is dead, so there you go. But nonetheless, we made it up the hill, so let's just carry on, shall we? Cornering of this thing is not ideal. Come on! But you can tell that it is very strong. Like orders of magnitude better than the previous motor. Look at this. I'm just slowly plowing through. Come on!
So while I get myself increasingly stuck in some vegetation, why don't we do some secondary school physics for a bit? I recorded some acceleration test footage of me on the skateboard, and this is what it looks like. As you can see, the skateboard actually gets going fairly well. Now, this wasn't quite at full power because I was worried about breaking the thing and I still needed to get back home on it, but it is almost at full throttle here. Now, if we go through this video frame by frame, we can actually record some very interesting data, which is what I've done here. So you can see I've labeled the frames of the video. I've converted that into the time in seconds, and then here is the position of the skateboard in pixels on the screen, which I've converted into centimeters and meters of distance. And using this information, we can make a very nice chart of the position of the skateboard, or the distance that it covered over time. So you can see there it goes. And of course, we can also convert that into the speed of the skateboard over time, which is this chart down here. So this is how fast we were going in meters per second over time in that video. Now, using some maths, we can convert this into the acceleration of the skateboard versus the time. So this is how many meters per second squared of acceleration I experienced. And of course, since acceleration, or since force is mass multiplied by acceleration, and the mass of the skateboard plus me on it is about 85 kilos, we can also plot the force applied to the skateboard while this acceleration was happening. Now actually, I've also added about 35 newtons of baseline force to this, because it turns out it requires about 35 newtons to get the skateboard to move in the first place, so to overcome the friction forces, you know, the rolling resistance of the tires and the drivetrain and all that. Now, of course, it's probably not entirely correct to assume that that's going to be a constant 35 newtons. It might also vary a bit depending on the speed. But for this, it's good enough, and we're going to assume that that is a constant force that applies all the time. Now, we know that in a mechanical system, power is force multiplied by speed. So if we take each one of these points, each one of these force values, and we multiply it by the values from our speed or velocity chart, we can get a power chart, which is what we have here. So this light green blue line, that is actually the mechanical power applied to the skateboard. But you can see that it is a very, very spiky chart. Like, it's all over the place, which it has to do mostly, I think, with measurement noise. me measuring the position of a skateboard in the video, and you can kind of see that happening here. This chart looks quite clean, this one starts becoming a little bit more noisy, and then this one is super spiky, and so is that one. And so basically each step along the way we're amplifying the noise until you end up with this mess. So I've run a low pass filter over this data, which is the dotted line you see here, to kind of smooth it out. That gives you a better picture of what the actual mechanical power might have looked like during that test. In this chart there is actually another line, which is this dark blue line here, which shows the electric power consumption of the motor. So during the test I also had a current clamp on the deck of the skateboard, which was measuring the current from the battery pack, and I also filmed the display of that current clamp so that I could plot the electric power consumption as well, which I've done here. So you can see that's this line here, and once again I've run the same low pass filter over it to smooth it out. So this shows you that the efficiency of our electric motor during this test was, I guess we could say, roughly around 50%, which is of course the combined efficiency of the drive and the motor. Now this is not fantastic, but you do have to realize this was with full power or nearly full power being applied, accelerating from a dead stop, which is, not amazing conditions for getting high efficiency from an electric motor. And this wasn't an efficiency test after all, it was a power test. But what I think is interesting about this chart is the drop in mechanical power that we see right around here. So at this point, the electric power actually goes up a bit more and continues to stay quite high, around 240-ish watts. But the mechanical power is it's about 125 watts, I suppose, and then it starts going down a bit, and the efficiency of the motor around this point absolutely tanks. I think the reason for this is that there is something wrong with my lookup table that I'm using to determine the firing angles. So in this motor, I'm using a system where the firing angle, so essentially the exact moment at which you switch on the next phase, that's variable, and it depends on the speed of the motor. So the faster the motor spins, the earlier you switch on the next phase to compensate for delays like the inductance of the motor windings and maybe some processing delays, some delay introduced by the encoder, that kind of thing. So the faster the motor spins, the earlier a phase gets switched on. And these values, so exactly how much earlier a phase gets switched on for a particular speed of the motor, is done using a lookup table. So there is a table of values stored in the controller, and that table just says, for this particular RPM, the timing advance should be this much, right? That's how it works. It's a very simple approach, and these values are basically determined through a bunch of trial and error. But this suggests that for the RPM that we reach around this region here, those values might be way off, right? Because the efficiency of the motor goes way down. And you can see in this chart here, in this one I've actually plotted the RPM in it as well. So you can see there's the RPM. I've divided it by 10 so that it fits on the scale a bit more neat. You can see right around this point, which should be around 1300 RPM or something. It's about 130 on this scale here. At that point, the efficiency becomes horrible for a bit, and so this zone here is where I need to tweak my lookup table for the timing values. And actually I've already kind of noticed this myself during the testing, where I would get on the skateboard, it would accelerate away quite well, and then the acceleration would plateau for a bit and it would really struggle to speed up anymore, even if I applied lots of throttle. And then, after reaching a certain speed, the acceleration would suddenly continue. And that point isn't visible in this chart because it didn't really happen before I was off screen in this bit of video. But I guess somewhere around here, you would see the acceleration climb back up, so the motor RPM would start to rise more steeply again. So anyway, it's kind of cool to be able to see from this chart where exactly we probably need to tweak the values in our controller. So that was, I thought that was kind of interesting to take a look at. Let's see if I got out of those woods yet.
This thing is going. I mean, it's not very fast, but then it's geared for off-road use anyway, so it's more of the tractor of skateboards, if you will. Right, so there it is, the new homemade electric motor. I think it did super well. Of course we had a little bit of issues getting up that steep hill, but that was more of a mechanical problem than one with the motor. It held up super well. Also, what you didn't see is that actually we went here with the cargo box on the skateboard with all the filming gear in it, or all the filming gear, okay, the camera, the rest of it was mostly food and some tools for emergency repairs, but guess what, we didn't need those tools after all. Also, it's like 30 degrees Celsius outside, so it's really hot, and yeah, okay, the motor is quite hot too. I guess about 70 degrees if I touch this, 70 degrees C, but nonetheless it's working fine, no overheating problems, so that's very nice as well. So I think the new electric motor did quite well. If you enjoyed this video, maybe consider clicking the like button, or maybe even subscribing to this channel. And of course, thank you very much for watching.